In this lecture we will study diode as a rectifier. In the last chapters we have already seen that what is a DC level of the waveform. Suppose we have this sinusoidal waveform, we already calculated the DC value for this waveform, and for this waveform we got the DC value equal to 0 volt or average value equal to 0 volt. And for this sinusoidal waveform we know that its RMS value is defined as Vrms equal to Vm by root 2. These are the this value is associated with the AC part of the waveform, and this is the DC value of the waveform. Now suppose we have a rectifier circuit. A rectifier circuit will be given an input like this. If this input is given to the rectifier, this rectifier, suppose we have this half wave rectifier, this will convert this input waveform into this waveform. Now this is the output waveform of this rectifier. If we calculate the DC value of this waveform, we get DC equal to 0 volt. But when we calculate the DC value for this waveform, we take the samples, positive samples, samples in positive half cycle, samples in negative half cycle. This is one complete cycle. During positive half cycle we get positive samples, and during negative half cycles all the samples are 0. If we take the average value divided by total number of samples, then we get a positive value, means the DC value for this waveform is non-zero, positive value. So now we can define a rectifier as a rectifier is a circuit which converts an AC signal with 0 DC level to a unidirectional, AC will be bidirectional, to a unidirectional signal with non-zero DC level. So rectifier will convert a bidirectional signal with 0 DC level to a unidirectional signal with non-zero DC level. Now we have this 3 signals. In this signal no part is changing, the waveform is constant for this signal. So for this signal, if we define the DC value, this DC value is defined as VDC equal to V. And the RMS value for this signal will also be this DC value V. This signal is called pure DC signal. Now this signal is pure AC signal, and for this pure AC signal this VDC value equal to 0 volt, and RMS value for this signal is Vm by root 2, where Vm is the maximum value for this signal. Now this signal has 0 DC level, hence called pure DC signal, pure AC signal. For this signal the DC value is not a 0. The sinusoidal voltage is oscillating around this voltage V, and it is going up and down around this value by voltage Vm. Now for this signal DC value VDC equal to V, and RMS value Vrms is not defined directly, but the RMS value for AC part is defined first, which is called V AC RMS, which is equal to the RMS value of this AC part. RMS value of this AC part, which is equal to Vm by root 2. And the total RMS value for this signal, which has DC value, also RMS value, called AC plus DC signal. For this signal, the RMS value is equal to under root of VDC square plus VAC RMS whole square. So this is the value, how this is how RMS value is calculated for AC plus DC signal. Now first we'll see a half wave rectifier. A half wave rectifier has a very simple circuit with one diode, now in this half wave rectifier, uh, this input voltage Vi, or it will be V1. Due to this V1 voltage, the transformer will have a secondary voltage V2 depending on the turns ratio. This voltage V2 upon V1 is equal to N2 upon N1. Now this V2 voltage will be a sinusoidal voltage which have this kind of waveform, means it has positive half cycle and negative half cycle as well. When V2 voltage is in its positive half cycle, the diode D is simply it is clearly seen that the diode D will be forward biased, and if diode D is forward biased, it will be replaced by a short circuit. It will be replaced by a short circuit, and a current will flow through this resistor, load resistor RL, which will deliver a voltage across this load resistor RL V0. Now when V2 increases, with increase in V2, the current through this load resistor RL also increases, and accordingly this voltage V0 increases, and we get a voltage V0 like a voltage V2. If V2 is increasing and decreasing, this voltage V0 is also increasing and decreasing with the input voltage. So this was the case during positive half cycle. This is the input waveform, or we will call it as voltage V2 at the input of this rectifier, or it is the secondary voltage of the transformer. During first half cycle, diode was forward biased and a pulsating current was there in the circuit, and a pulsating voltage was obtained across the load resistor. Now during negative half cycle, the polarity of the input will be reversed and the diode in the circuit will be reverse biased. If diode is reverse biased, it will be replaced by a short circuit, open circuit, and the voltage across the load resistor will be zero as there is no current in the circuit. So I into RL output voltage will be zero. So in this way we will get this waveform. Now for the input waveform, which is a full sinusoidal voltage, we have DC value equal to 0 volt because it is oscillating around 0 volt, and the RMS value for this waveform is Vm by root 2. For the output voltage V0, the negative half cycle voltage is absent, only the positive half cycle voltage is there. So For this output waveform, output voltage waveform, the DC value is non-zero, and using the equation for DC calculation, we get this DC value VDC equal to Vm upon pi. This is the 2 pi angle, this is pi angle, and this value is Vm by pi. This is the maximum voltage Vm, this is the maximum voltage Vm, and the RMS value for this voltage is Vrms equal to Vm by 2. These two values are calculated using the equation. Equations are not important. These values, these formulas are important for this output voltage of the rectifier. Now we'll define next we will define ripple factor. Ripple factor. Ripple factor is the it is the measure of variations of output signal with respect to its DC value, with respect to its DC value. Mathematically, this ripple factor R is given by VAC RMS divided by VDC. We know that VRMS equal to under root of VDC square minus plus VAC RMS whole square. Now from this we can write that VAC RMS equal to under root of V under root of Vrms square minus VDC square. So the ripple factor R will be equal to under root of Vrms square minus VDC square divided by VDC. Now the ripple factor will be Vrms upon VDC whole square, because if this VDC is taken in the root, it becomes square, minus VDC upon VDC whole square. It is Vrms upon VDC whole square minus 1. So this is the ripple factor, and for this half wave rectifier we have got this Vrms equal to Vm by 2 and VDC equal to Vm by pi. If we substitute these two values here, Vrms equal to Vm by 2 and VDC equal to Vm by pi. If we substitute these two values here, square minus 1, we get under root of pi square by 4 minus 1. After solving this, we get ripple factor R equal to 1.21. So this is the ripple factor of half wave rectifier. Now by calculating the ripple factor, we can compare two rectifiers by if the ripple factor is more, means there is more variation in the output with respect to a DC value. Now second, we will calculate efficiency of a rectifier. Efficiency of a rectifier is the ratio of output DC power by input AC power. Means we are supplying input AC to a rectifier and it is converting it into DC, pulsating DC. Now we will calculate the power which is available at the output and the power which is supplied to the rectifier, and based on this we will calculate its efficiency in percentage. Output DC power, simple, it will be calculated as the product of output DC voltage into output DC current, while input AC power will be the product of RMS value of input voltage and RMS value of input current. Now again see the rectifier circuit, and we will change a little bit in the equations. Now in this, the voltage V2 is the input voltage to this rectifier, and for this voltage V2 we have this waveform, and it has a maximum value Vm. For this output voltage V0, the waveform is like this. Only voltage is obtained for only half cycle, and for this the voltage is Vm dash. Suppose it is Vm dash, maximum voltage. Now if this voltage is applied at the input, some part will be dropped across this this diode, because up to now we have considered that this diode is ideal, but practically it will have some voltage drop, and the remaining voltage will reach up to the load resistance. Also there will be some voltage drop across this winding, so the Vm dash value will be less than this Vm value. So we are getting two different maximum values in this circuit. The maximum value of the input voltage V2 and the maximum value of output voltage, both are different. Also the waveform of these voltages are different, but one thing is same on input and output both, which is the current of the circuit, which is flowing for only half cycle. Only for half cycle same current is flowing through the input and same current is flowing through the output. So current through this circuit will be same at all the instants. So now we have got a parameter which is same at all the time through this circuit. So we'll do all the calculation regarding efficiencies in the form of current only. So now we'll define the output DC power in terms of the current only, that is IDC square into RL, because we are taking output only across the load resistance. But the input power is supplied at the input, which is going to the winding, to the diode, to the load resistance, means the input power will be the sum of the power consumed by all these three components. So input AC power equal to I RMS square into RS, the winding resistance, RF, the forward resistance of diode, plus RL, the load resistance. This is the power, total power supplied to the circuit, and output is obtained only across the load. Now the efficiency will be equal to IDC square into RL divided by IRMS square into RS plus RF plus RL into 100%. Now in this circuit, the waveform for the current is drawn here. This is half sinusoidal voltage, half sinusoidal current, and you know that for half sinusoidal current, the DC current, DC value IDC will be equal to Im by pi, and RMS value is equal to Im by 2, just like the voltage. Now substituting all these value, IDC equal to Im by pi whole square into RL divided by Im by 2 whole square into RS plus RF plus RL into 100%. Now cancelling these, we get 4 upon pi square into RL upon RS plus RF plus RL into 100%. Now if you take these two values, RS equal to RF equal to 0, if both are 0, then we can say that efficiency will be maximum. So for maximum efficiency, RS equal to RF equal to 0, and maximum efficiency will be equal to 4 by pi square into RL upon RL into 100% will be equal to nearly 40.6%. So this much is the maximum efficiency of a half wave rectifier. Means nearly 60% of the power is consumed by the circuit, only 40% is delivered at the output, and this too is a extreme case. The actual efficiency is less than 40. Now the next is peak inverse voltage. Peak inverse voltage for a circuit is uh, peak inverse voltage is the maximum voltage that appears across the diode when it is reverse biased. For example, this is the circuit for half wave rectifier. We know that the diode is reverse biased during negative half cycle of the input. Now suppose we have this negative half cycle and input is at its maximum value Vm. Diode will be reverse biased, so it will act as open circuit. If it is acting as open circuit, will have a voltage like this with polarity like this, and when input is maximum, the voltage across the diode will also be maximum. And we know that the current through this circuit I equal to 0, so there will be no voltage drop across this resistor. So there will be only two voltages in the circuit. Now when we apply KVL in the circuit in the loop like this, so we get minus Vm plus PIV equal to 0. So PIV equal to Vm. So in this circuit, the maximum value that appears, the maximum voltage that appears across the diode when it is reverse biased is equal to the maximum value of input voltage Vm. So if input is 10 sin omega t, the maximum voltage across the diode will be 10 volts. So we will use such a diode in the circuit which can withstand in the circuit for 10 volt in the reverse bias. It should not break down or it should not burn, otherwise it cannot be used as a rectifier. Now the next is transfer characteristics for the circuit. Transfer characteristics. Suppose we have this circuit. In the circuit, this voltage will be the input voltage, though we were calling this voltage equal to V2, but now we will call this as input voltage, and this is the output voltage of the circuit. It is clearly seen that if input Vi is less than 0 volt, means negative half cycle, for negative half cycle diode D is reverse bias, and if diode D is reverse bias, there is no voltage obtained at the output. So V naught equal to 0 volts. Second case, if Vi is greater than equal to 0 volt, this diode will operate in this circuit. That is, diode will be forward biased. If the diode is forward biased, there will be a voltage at the output which will be equal to input. If the winding resistance, winding drop and diode drop are neglected, then output will be input voltage. So now for this circuit we will draw the transfer characteristics. Sorry, this is input voltage, this is output voltage. Break voltage is 0 volt. For Vi less than 0 volt, output is 0 volt. So this will be the output voltage. Now for Vi greater than 0 volt, output equal to input. When output equal to input, we know that the graph will be a straight line passing through origin. This kind of voltage will be obtained. So these are the transfer characteristics for a half wave rectifier.